Now here's a fun little exercise. The fastest spacecraft we've ever built is Voyager 1. Beautiful machine, been going for decades. You know how long it would take Voyager 1 to reach Proxima Centauri? 73,000 years. 73,000. That means if your great-great-great ancestors had sent Voyager when the pyramids were being built, it still wouldn't be there yet. The problem is distance. Raw, incomprehensible distance. That's the first fundamental problem we have to deal with, and no amount of cleverness is going to make it disappear. You can't negotiate with the universe. You can't find a loophole. The distances are what they are. So what do? Well, the only thing we can do is go faster. Much, much faster. And here's where the physics gets interesting. Because when you start thinking about going really fast, I mean really fast, like a significant fraction of the speed of light, you run smack into some problems that aren't immediately obvious. The first problem with going fast is energy. Just enormous amounts of energy. Let me give you a sense of the numbers. Our best rockets today use chemical propulsion. You burn some fuel, you get hot gases, those gases push you forward. It's simple, it works, but it's fundamentally limited. When you use chemical rockets, even the most optimistic calculations show you can maybe get a spacecraft up to something like 20 kilometers per second. That's pretty fast, right? Hundreds of kilometers per second for some theoretical concepts. But the speed of light is 300,000 kilometers per second. You see the gap? It's not small. To get a spacecraft moving at just 10% of light speed, and that's still nowhere near fast, you'd need more energy than humanity currently uses in a year. And you need to carry that energy with you, or have some way to get it to your spacecraft continuously. This is the fundamental problem. Energy scales as the square of velocity. Double your speed, you need 4 times the energy. If you want to go 10 times faster, you need 100 times more energy. This is not a small inconvenience. This is a hard physical wall. Now, engineers and physicists, being clever people, have thought about different ways to get around this. One approach that's gotten quite a bit of attention is nuclear fusion rockets. See, in the core of the sun, hydrogen fuses into helium, and this releases enormous amounts of energy. If we could somehow harness that same process in a rocket, we'd get something very different from chemical rockets. Here's why it's attractive. Fusion can give you far more energy per unit mass of fuel than anything we have today. It's the closest thing we have to a serious solution for getting to nearby stars and timescales that make some kind of sense, decades instead of millennia. But, and this is a big but, we don't actually know how to make a nuclear fusion rocket work. We've been trying to control fusion for the better part of a century, and we still can't do it reliably on Earth, let alone in the confined space of a rocket engine. Getting temperatures hot enough to fuse hydrogen, keeping them stable, maintaining the reaction, it's fiendishly difficult. And here's something people don't always think about. Even if we solve fusion, you still have the problem of acceleration time. Say you've got this fantastic fusion rocket that can accelerate your spacecraft at 1 gravity. That's 1 g, the same acceleration you feel sitting in a chair right now. How long does it take to reach, say, 1/10 of light speed? Well, basic physics tells you that takes about a year. But then you have to decelerate when you arrive, another year. So you're looking at 2 years just to speed up and slow down for a journey that'll take decades with relativistic effects. For journeys to farther stars, it's even worse. The energy required becomes almost incomprehensible. Then there's the problem of cosmic radiation. Space is not the nice, empty void that people imagine. It's filled with high-energy particles, protons, cosmic rays, all sorts of nasty stuff. On Earth, we're protected by our magnetic field and our atmosphere. In space, there's nothing to protect you. These particles smash into your spacecraft at tremendous speeds and can damage it and damage any living things inside. Protecting against this requires shielding, and shielding is heavy. Heavy things are hard to accelerate. You see how the problems pile up? Every solution creates new problems. Now, some people have proposed other solutions. Light sails, for instance. The idea is simple and elegant. You use a powerful laser to push on a thin, reflective sail attached to a small spacecraft. Since light carries momentum, yes, light, which has no mass, still carries momentum. That's one of those neat things about physics. The laser pushes the sail forward. No fuel needed on the spacecraft at all. The appealing thing about light sails is that they're based on physics we understand completely. There are no mysteries no unsolved problems about the basic mechanism. You can do this today with existing technology. And people have actually proposed a real mission called Breakthrough Starshot that would use this approach to send tiny probes to Alpha Centauri at something like 20% of light speed. But here's the problem. Those probes are tiny. We're talking about 1-gram spacecraft. Tiny little things. They could maybe send back pictures or data. But scaling this up, getting a spacecraft big enough to carry people or cargo or equipment, becomes exponentially harder. The laser you'd need would be absolutely enormous. The engineering challenges would be immense, and the questions about how to protect the spacecraft and its contents from impacts with even tiny particles at those speeds. We don't have good answers yet. There's also the simple problem that the laser beam spreads out as it travels. Light intensity decreases with the square of distance. So as your spacecraft gets farther and farther away, the push gets weaker and weaker. You could potentially overcome this by using shorter wavelengths or larger sails, but we're just moving the engineering problem around, not solving it. Now, some people, and here's where we get into more speculative territory, some people ask, why do we have to go through space? Why don't we just go around it? And they're referring to ideas from Einstein's general relativity about wormholes and warp drives. Let me explain what these are, because they're actually pretty fascinating, even if we don't know if they're really possible. Einstein's theory of general relativity says that space and time are not rigid things. They're flexible. They can bend and curve and stretch. In extreme conditions, near a black hole, for instance, space-time gets seriously warped. And mathematically, if you write down the equations of general relativity, there are solutions that describe tunnels through space connecting two distant regions. These are called wormholes or Einstein-Rosen bridges if you want to be fancy. Now here's the thing. The equations allow for them. Mathematically, they're possible. But physically, that's a different question. Every time physicists look at the details, they run into problems. The biggest problem is that wormholes appear to be unstable. They'd snap shut almost instantly. To keep one open, you'd need something called exotic matter, stuff with negative energy density. That's not something that exists in any quantity we can access. It might not even exist at all. It's a term physicists can plug into equations, but whether it's real is an open question. Similarly, warp drives, the idea that you could create a bubble of warped space-time that carries your ship faster than light without violating relativity. Well, they have the same basic problem. The math works if you allow exotic matter with negative energy, but we have no idea how to create that, or if it's even possible. Here's something important to understand. Just because something doesn't violate the equations we have doesn't mean it's possible. There are a lot of things that are consistent with our theories that nature apparently doesn't allow. The fact that the math works is only the first step. You have to actually be able to build it, and physics often says no to lots of mathematically possible things. There's also something called the Casimir effect, which does suggest that negative energy might exist in some form. But the amounts we're talking about for interstellar travel, the amounts you'd need to keep a wormhole open or generate a warp field, are absolutely astronomical. We're talking about energy equivalent to entire planets, maybe entire stars. So let's step back and think about what's actually feasible with the knowledge we have now, or likely to develop in the near future. The most straightforward approach, the one that doesn't require us to solve impossible physics problems, is just to go slow and bring a lot of people. This is the idea of a generation ship. You build a massive spacecraft, stock it with supplies, launch a large population, and people live their entire lives on the ship. Your great-great-grandchildren finally arrive at the destination. It's not glamorous, but it works. The advantage of this approach is that it only requires technology we basically understand now. The challenges are biological and psychological rather than physics-based. How do you keep a closed ecosystem functioning for centuries? How do you maintain a functional human society on a ship in complete isolation? These are hard problems, but they're engineering and biology problems, not physics problems. Another approach is hibernation, cryosleep, people call it. If we could learn to freeze people safely, slow their metabolism to almost nothing, then wake them up when you arrive, you've solved a lot of problems. The ship doesn't need to be as large. The psychological strain is eliminated. But here's the catch. We don't know how to do this. We can't even do it reliably with small mammals yet, let alone humans. The ice crystals that form destroy cells. We need fundamental advances in biology and medical technology that we can't even see the path to right now. There's also something that gets mentioned sometimes: relativity time dilation. If you're traveling at a significant fraction of the speed of light, say 90% or more, time actually passes more slowly for you relative to someone on Earth. So while a century passes on Earth, maybe only 10 or 20 years pass for you on the spacecraft. From your perspective, you've made much faster progress. But here's what's subtle about this. You still need to generate the energy to accelerate to those speeds, and you still need to survive the journey. The time dilation is real, but it doesn't change the fundamental energy requirements. It's an interesting bonus feature, but it doesn't solve the core problem. So where does this leave us? What's the actual realistic path forward? I think the honest answer is that we don't know yet. We're not at a dead end, but we're facing fundamental constraints that aren't going away. What we need is either 1. A breakthrough in propulsion technology that we can't even imagine right now. Some completely new physics that we haven't discovered yet. 2. The ability to harness truly enormous amounts of energy. Fusion on massive scales, maybe, or antimatter, or something else entirely. 3. A way to solve fundamental biology problems like controlled hibernation that we currently have no path to. Or 4. We accept that interstellar travel just takes a very long time, and we build generation ships and populate them with people who understand that their descendants will arrive, not them. And here's something else to think about. Space is really big, vast. Our galaxy is 100,000 light years across. The nearest galaxy is 2 million light years away. Even with the wildest theoretical technologies we can imagine, warp drives, wormholes, antimatter engines, we're talking about civilizations that are so far beyond us technologically that it almost defies imagination. We can't even conceive of what would be possible. But there's something interesting about that. See, this is where the Fermi paradox comes in. If interstellar travel is possible, even just barely possible, then over billions of years, civilizations should spread throughout the galaxy. They should be everywhere. We should see evidence of them. But we don't. We haven't detected any radio signals from extraterrestrials. We haven't seen any signs of their activity. There are explanations for this, of course. Maybe life is rare. Maybe intelligent life is even rarer. Maybe civilizations destroy themselves before they can spread. Maybe there's something about the laws of physics that makes interstellar travel impossible that we haven't discovered yet. Or maybe we're just looking in the wrong way. But one possibility that's worth considering is that the Fermi paradox tells us something. Maybe interstellar travel is really hard. Maybe it's so hard that civilizations essentially never do it. Maybe there's some fundamental barrier we haven't thought of yet. The universe is under no obligation to make things easy for us. Now, let me tell you what I find genuinely exciting about this whole question, and it's not the prospect of flying around the galaxy. It's the problems themselves. Every single obstacle we've talked about, the energy requirements, the radiation shielding, the propulsion challenges, the biological problems with long-duration spaceflight. Every one of these forces us to think deeply about how nature works. To solve the energy problem, you need to understand nuclear physics in detail. To protect against radiation, you need to understand particle physics and material science. To build stable life support systems, you need biology, chemistry, engineering. These are some of the deepest questions we can ask. And here's the thing. Many of the technologies developed to pursue interstellar travel will have practical applications here on Earth. Better materials, more efficient energy production, advances in medicine and biology. These things have value independent of whether they get us to the stars. So even if we never leave the solar system, even if we decide that interstellar travel is just too hard, the pursuit of it pushes us forward scientifically and technologically. Let me say something about the actual current state of the art, because it's worth understanding what we're actually capable of right now. We have ion drives that are incredibly efficient. They use electric fields to accelerate charged particles, usually xenon, to very high speeds. They produce very low thrust, but they can run for months or years, continuously accelerating a spacecraft. There are several spacecraft in the solar system using ion propulsion right now, and they work beautifully. But even ion drives don't get you to interstellar speeds in any reasonable time frame. We have proposals for more powerful nuclear propulsion systems. These have been designed and analyzed, but never built. Nuclear thermal rockets could work in principle. heating propellant using a nuclear reactor and expelling it at higher velocities than chemical rockets allow. And there are genuinely interesting theoretical proposals like the one I mentioned earlier, Breakthrough Starshot, which proposes using a massive laser array on Earth to push tiny, lightweight spacecraft. This could actually work, and it could get small probes to nearby stars within our lifetimes. The first results could come back within decades. That's genuinely achievable technology. But when you start talking about transporting people, carrying enough supplies for a long journey, protecting against radiation, keeping people alive and psychologically stable, that's when the problems multiply. You know what I think is the most likely near-term scenario? I think we'll send robotic probes first. Probably small, lightweight probes using some kind of advanced propulsion, light sails, laser-pushed craft, something like that. They'll take decades to get there, but that's fine. Robots don't care. They'll send back pictures, data about the planets, information about atmospheric composition and surface conditions. And then, once we know there's something worth going to, maybe a habitable planet, maybe something that looks promising, maybe at that point, 100 years from now or 500 years from now, we'll think about sending people. And when we do, it'll probably be on a generation ship. A big spacecraft, self-sustaining, with a complete civilization aboard. It's not very glamorous. It doesn't make for exciting movies. But it's the kind of thinking that takes the actual constraints of physics seriously. The universe doesn't care about our schedules. It doesn't care that we want to reach another star in a human lifetime. Nature follows the rules it follows, and those rules are indifferent to our desires. That's the first thing you have to understand if you want to think clearly about this problem. And here's what's fascinating. Those rules are not arbitrary. They make sense. They're consistent. They have a kind of beauty to them. The fact that energy scales as the square of velocity, the fact that acceleration requires continuous application of force, the fact that mass and energy are equivalent, these aren't bugs in the system. They're features. They're how the universe actually works at the deepest level. Understanding why these rules exist, what they imply, how they constrain what's possible, that's the real joy of physics. It's not about getting somewhere. It's about understanding how things work. So the question of interstellar travel is really a much deeper question. What does nature allow? What are the actual limits of what's possible? And are those limits what we think they are? Or are there surprises waiting for us? We don't know yet. And that's what makes it interesting. One last thing I want to mention. There's something called the Tsiolkovsky rocket equation that governs how spacecraft work. It relates the change in velocity you can achieve to the exhaust velocity of your propellant in the mass ratio. That's the initial mass divided by the final mass. And this equation tells you something profound. To get significant velocity changes, you need either very high exhaust velocities or very large mass ratios, preferably both. For interstellar velocities, this equation tells you that you need absolutely enormous amounts of fuel, or you need exhaust velocities approaching the speed of light. Chemical rockets just can't do this. You'd need something more. And that something more is what we're still searching for. Different approaches have different advantages. Fusion rockets offer high specific impulse. Antimatter engines would be even better, but we can't produce and store antimatter in meaningful quantities. Light sails don't require any onboard fuel, but they have other limitations. And then you get into the truly speculative stuff. Wormholes, warp drives, where we're not even sure the physics works the way we think it does. What strikes me most about all of this is the honesty required to think about it properly. We don't have the answers. We don't have a clear path forward. And that's okay. That's how science actually works. You look at a problem, you do the best you can with what you know, and you admit what you don't know. I've spent my life doing that, and I've never found a problem that didn't become more interesting once I understood how much I didn't understand about it. Interstellar travel is the same way. The more you look into it, the more complicated it gets. But that complication isn't a reason to stop thinking about it. It's a reason to think even harder. Because somewhere in all those complications might be something important. Either a solution we haven't thought of yet, or an understanding that changes how we see nature itself. And that's what it's all about, really. Not getting to the stars. Understanding the rules that govern everything, including whether we can get to the stars or not. Understanding nature as it actually is, not as we wish it would be. That's the lens through which I try to look at every problem. And it's the lens through which I'd encourage you to look at this one.